Inside this enormous semiconductor factory, some of the most advanced machines ever built are working around the clock. Their mission is to manufacture the processors that power modern artificial intelligence. These tiny chips train language models, generate images, control autonomous machines, analyze scientific data, and operate some of the world's most powerful supercomputers. A finished AI accelerator may fit inside the palm of your hand, but inside it are billions of microscopic transistors, multiple layers of metal wiring, and several stacks of ultra-fast memory. Producing one requires purified silicon, extreme ultraviolet, light, plasma, ion beams, atomic-scale deposition, precision robotics, and production environments far cleaner than a hospital operating theater. One tiny particle can ruin an entire processor. One manufacturing defect can affect hundreds of chips on a single wafer, and one completed wafer can represent millions of dollars in potential computing hardware. This is how NVIDIA-style AI chips are mass-produced inside a multi-billion-dollar semiconductor factory. The journey begins long before any physical chip is created. Teams of engineers first design the processor using powerful electronic design software. They determine how many computing cores the chip will contain, how data will move between them, and how the processor will connect to external memory. Unlike a conventional computer processor, an AI accelerator is designed to perform huge numbers of mathematical calculations at the same time. Thousands of specialized computing units process matrices, vectors, and tensors, the mathematical structures used by artificial intelligence models. The design may also contain cache memory, video processing circuits, communication links, security systems, and power management components. Every transistor and electrical connection must go inside a crystal growing facility. Purified silicon is placed into a large quartz crucible and heated until it melts. A small seed crystal is lowered into the molten silicon. The seed is then slowly rotated and pulled upward. As it rises, the liquid silicon solidifies around it, following the same crystal structure. Over many hours, this process creates a long, perfectly organized single crystal silicon cylinder known as an ingot. The ingot may be approximately 300 millimeters in diameter. Robotic systems inspect its shape, diameter, and internal crystal quality. The ends are trimmed, the surface is ground into a uniform cylinder, and a small orientation notch is added along one edge. The ingot is then transported to an automated slicing machine. A multi-wire saw uses many extremely thin wires to cut the crystal into hundreds of circular discs. These discs will become the wafers on which the AI processors are manufactured. Freshly cut wafers have rough and uneven surfaces. Their edges are rounded to prevent cracking. Automated lapping machines remove surface damage and bring each wafer to a consistent thickness. The wafers then undergo chemical-mechanical polishing. Each wafer is pressed against a rotating pad while a carefully controlled chemical slurry flows across the surface. This process produces an exceptionally flat, mirror-like finish. Flatness is critical because later machines must focus microscopic circuit patterns across the entire wafer. After polishing, high-purity water and specialized chemicals remove particles, metallic contamination, and organic residue. Optical inspection systems scan each surface for scratches, pits, and crystal defects. Only wafers meeting the required standard continue into fabrication. The approved wafers arrive at the semiconductor fabrication plant, commonly called the fab. This facility may cost more than $10 billion to build and equip. Beneath the production floor are enormous networks of pipes carrying ultra-pure water, vacuum, chemicals, and specialized gases. Power systems deliver extremely stable electricity to thousands of precision machines. Air handling systems continuously filter and circulate the cleanroom air. Workers wear full-body cleanroom suits, gloves, masks, hoods, and boots. These suits are not mainly designed to protect the workers from the chips. They protect the chips from the workers. Human skin, hair, and clothing constantly release microscopic particles. Any one of those particles could block a circuit feature or cause an electrical short. The wafers travel through the factory inside sealed containers. Overhead, robotic transport systems carry these containers between machines. A central manufacturing system tracks every wafer and controls which process it receives next. Production does not move in one simple straight line. Instead, wafers travel through a complex network of deposition tools, lithography systems, etchers, furnaces, implantation machines, and inspection stations. The first major objective is to create the transistors. A transistor acts like a microscopic electrical switch. By switching on and off billions of times per second, groups of transistors perform calculations and store information.
This cluster here is a priority.
Agreed. What's the total impact?
It's pushing the defect rate up.
Let's log it. Fans are stable, lights are green.
Confirmed. Throughput is nominal.